what I have is high voltage over here on this side. So I would connect this. If you want high voltage, do you connect this side to your positive end of your battery or your negative end of your battery? Positive. Notice that I want the positive charges to run away from high voltage, so I got to put the positive end this way. Low voltage, I'd have to use the negative end of my battery. So this would be the negative side right there. And what I've got is an interestingly shaped tube or conducting wire here. It's got two areas. It's got A1 over here. It's got A2 over here. Here's my question to you. How do the drift velocity, the current density, the current, the electric field, and the resistivity vary as I go from here to there? So we're going to ask all these one at a time. How do each of these change? So to see this, let's start with the current. Let's say I've got current I at this point. Current I is right there. My question to you, the first question is, how does the current down here at this end compare? So let's see what your intuition is. First, will the current coming out here, right there, will that be thumb up if higher, thumb down if lower, thumb sideways if the same? Go ahead and vote there. The question is, if I've got current I at this point in this weirdly shaped funnel conductor, is the current here, thumb up for higher, thumb down for lower, thumb sideways the same? Okay, so here's what we're going to do. I'm going to pause this and we're going to do a little demo. And we can compare current coming out, the current right at this point to the current coming out of this narrow end. Electrons, like water, are not compressible. Because basically, you can have one electron per atom. You can't crowd them on there. If you get more electrons on one atom, that electric field will push them away from each other. They hate each other. So water is like electricity in so many ways. So I'm gonna get 250 milliliters to go out from there to there. Let's see what happens right here. And any predictions as to how much current came out this end?
250 milliliters.
And sure enough, 250 milliliters is what it's at right there. So now we can answer our question, how does the current at one end of that conductor compare to the current at the other end? The current stays constant. That was the demo that we just did. The current is a constant everywhere. If you got current I there, the current over here, this will also be I right there. That same current I coming out of that end. That allows us to get the next one pretty easily. My next question is, what happens to the current density? Thumb up if the current density goes up, thumb sideways if the current density stays the same, thumb down if the current density goes down right here compared to the end. In other words, how does the current density at this point compare to the current density right over here? Well, look at the cross-sectional area that this thing has to go through. Here's the cross-sectional area right there. Here's the cross-sectional area right there. What's happening to the cross-sectional area? It's getting smaller. So that means that the current density is I over the area, the cross-sectional area. As the A gets smaller, the current density, J, gets larger. Current density gets bigger. Now, next question. I'm jumping around here. I'm doing them in order that's we're gonna be able to get easily. The resistivity. And so let's talk about resistivity, and then we can instantly talk about the conductivity. What happens to the resistivity as you go from over here to over here? What does resistivity depend on? Materials. Does the material change? No. Resistivity, and for that matter, conductivity, they depend on the material, so they remain constant. Resistivity, conductivity, they remain constant. Now, here's the fun and interesting part. What happens to the electric field strength as you get from here to over here? Here's what I want you to do. I want you to use Ohm's law, and we are using this form of it is probably the easiest. This form of it to tell me what happens to the electric field, and then I will show you a more conceptual way to determine what happens to the electric field. Well, notice that the current density increases. Does the resistivity change? No. What has to happen to the electric field? It has to increase. And let me show you, that's right here, electric field gets higher. Let me show you a model using electric field lines that show you that. What happens is, I'm going to use my red lines here. The electric field lines actually do the following. They start off over here like this. Here's the electric field lines. They have to stay within this conductor. So in order to stay within the conductor, notice that they have to get closer together to stay within the conductor. So you can see that the electric field lines, using this awesome model of the electric field lines, it gets stronger. So the E field over here is weaker. E field over here is stronger. And that's the only way you can get your current density to be increased there, is with a stronger electric field. Okay, now for the final one on this page, what happens to the drift velocity? What happens to the drift velocity? My favorite way to look at this is right here, looking at this right here. Check out this. The current density is equal to the charge carrier density times the charge of the charge carrier times the drift velocity. Question, does the concentration of charge carriers change as you go from the wide end to the narrow end? Does little n change? Is water or electrons compressible? No. N is a constant. You can't change the number of electrons per atom. You can't change little n. That's constant no matter what the thickness of the material is. Is our elementary charge going to change? No. What's the only thing that can change if you're changing the charge, the current density rather? The drift velocity. Thumb up if the drift velocity goes up. Thumb down if the drift velocity goes down. Thumb sideways if the drift velocity stays the same. As our current density increases, the drift velocity goes up. It gets faster. It's the same way with water. Now, big advantage here to the people who are also taking the B exam, because we have, or the 1 and 2 exam, what equation is the same for fluids that it is for electricity? Who remembers the name of that? Yes, A1V1, the area 1 times the velocity 1 of water equals A2V2. That is called the continuity equation. As you get to narrower parts of a pipe, the water has to move faster because water's not compressible. Here, as you get to narrower parts, even the electrons move faster. Basically, just like water molecules, the electrons go faster as they get to a narrower spot.